Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at OneSpin with Tobias Welp, who's going to talk today about how you verify that the RTL created by designers actually matches what goes into an FPGA. What type of problems do people typically run into?
Yeah, so the situation people will be in is that they have an RTL. They use an implementation tool, which could be a synthesis tool, a place and route tool. And they want to check that what the implementation tool created is the same as what they actually use as specification, that the RTL, the original RTL, which they may have used quality assurance on, or that they are confident about the RTL, they're not confident about what the synthesis tool or the implementation tool in general.
Why don't you draw this out for us?
Sure. So assume, so you're starting at an RTL. So I'm going to draw like a very simple example of RTL here. So the example is going to have two state elements, which I'm going to write as this. We also assume that there's two inputs, some primary inputs. So I call them I1 and I2. So there may be some logic functions between here. I'm not going to draw what logic function is because it doesn't really matter here. But the output of this logic function is going to be provided to the state element. Let's assume that here at the output of this state element, which I'm going to call R1, is sent to another logic cloud. And the output of this logic cloud is first a primary output, which I'm going to call, let's just call it O. And then let's assume too that this logic cloud is feeding back into itself after going through another state element, which I'm going to call as R2.
So the user puts this into an implementation tool next, right?
Yes, that's correct. So let's draw this here as being, this is what the implementation tool does. And then the implementation tool is going to do something to the circuit, to the design. So most of the time you can expect that these logic clouds that we have seen here, they're going to be somehow modified. So let's give that thing a name, so let's call it F1 for the first logic cloud. This is going to be a different logic cloud than the one we have over there, so I give it like a little R in the. By the way, I'm going to use like these suffixes here to indicate which one of the revised as a revised side, which I'm referring to, and on the other side I'm going to use G suffixes to indicate the golden ones, because they are not the same. So most of the time, such an implementation tool is going to keep the state elements as they are. There are exceptions to this, but let's for now assume that they don't change. So there's another logic cloud here. Again, it may have a different implementation than the one on the golden side we have seen earlier. So therefore I'm giving it also the suffix. And then there's the output, which we hope is equivalent to the one on the golden side, but which may be different, and this is what we want to check out with the verification tool. So this is going to look like this then.
And the key here is to match them. How do you know they actually are matching?
Yeah, that is where the verification tool comes into play. So a verification tool usually use some proof engines. These proof engines, they implement certain algorithms. Many of them have been published in academia. A notorious one would be property-directed reachability, or IC3. But to use one of these back-end provers, one need to create a proof obligation first. And the most simple way of writing down this proof obligation in this case is by saying, well, I assume, so I'm assuming something, so let me write down here the assumption. So we are assuming that the inputs are equivalent. So this would be I1 G is equal to I1R, and the same thing for the second input. And once I'm assuming something, I could tell the backend prover check if the following assertions is true, and the assertion in this simple example would be that the output are equivalent. So you can give this proof obligation to a backend prover, and the backend prover is going to tell you yes, they are equivalent, or they are not equivalent, and in case it would tell you they are not equivalent, it would provide a counterexample which would help you to debug the inequivalence between the two.
What goes wrong here? This doesn't always work out as planned, right?
Yeah, the good news about the setup is that it's very general. So this works, I mean, the synthesis tool could do whatever it wanted, the implementation tool. It's also relatively easy, so as long as you have the proof, the backend, then this is going to work. You just need to figure out which are the matching inputs and which are the matching outputs. The problem here is scalability. And what I mean with scalability, let's draw a little diagram here. So we have on the x-axis the design size. And then on the y-axis you would have the verification runtime. So and then what you would get for this approach, which I'm calling the fully sequential approach, you would get a runtime which kind of looks like this. So with increasing design size, the verification runtimes grows exponentially. So this is, first of all, not something which to be super concerned about, because in general verification runtime increase exponentially with the design size. But the problem here is if you do this on this way, like there is something which I would call the industrial design size, so what like an industrial user would really require. And this industrial design size would be in almost all cases somewhere around here. So for this reason, this approach generally won't work in practice.
So how do you solve that? Well, what's the workaround?
Yeah, the workaround here is that you need to give some hints, some information to the prover. And as I alluded to in the beginning, the structure between the RTL and the revised design, I should write that down here. They are like similar. So you have still, even though the logic clouds they may have changed, you still have that with respect to the sequential gates. They are like at the same location, so they have a structural similarity. And this structural similarity you should let the tool know about. So how you can reflect there is that you write down exactly how it is in this case. So in addition to specifying that the inputs are equal, you could also say, well, the outputs of those flops, they're probably equal too. So let's assume this. So I would write down that R1G and R1R and R2G and R2R, that they are equivalent. This is an assumption which the prover would use. And then you need to write down an assertion too. Otherwise, it may be an invalid assumption. So you need basically to prove that the assumption is correct. And the way how you would do this here is that at the inputs of the flops, the next state value, they need to be proven to be equivalent at all times. So this adds like additional assertions here. In this case, the ones you are adding here would be that the next state, I'm going to indicate that with little ticks here on the golden and on the right side are going to be equal, and the same thing for the second flop for R2. So this part here, let's frame that. This is in academia generally referred to as an inductive invariant. It's an inductive invariant because it's always true, so that means it's invariant. It's inductive because assuming this is sufficient to prove it in the next state.
Is the inductive invariance always complete?
No, not in all cases. So the problem here is for a tool to figure out that these R1 on the goal and on the revised side, that they are actually the ones which are corresponding to each other. I mean, in this toy example, it's kind of obvious. And it's also obvious because of the indices, but in general, the naming rules from an implementation tool may be difficult. So, and also like an implementation tool generally does not preserve the structure completely, so it may actually do move flops around. Like for instance, a common scheme would be that like maybe these two flops would be moved after this logic cloud, which would be typically referred to as retiming, or even more complex optimizations. For instance, a shift register could be transformed into a RAM implementation or something of the like.
This is basically not for beginners, right? You really do have to understand what you're doing with these tools, and also with really understanding the code that goes into the where the problems potentially can be, how to optimize it along the way.
Yeah, so the tool, the verification tool, will generally try to figure out most of this correspondence by itself. But in general, it helps, and it may be necessary to add parts to the inductive invariant manually too. This inductive invariant is not complete, which may be the case in practice, because the transformation the implementation tool is doing is not fully understood. Then you can end up in a situation that this inductive invariant here, which I wrote down, is not complete. So let's assume that the R1 is found to be here, but the R2 is not. In this case, you would end up with an inductive invariant, which is just the R1 part, and you would also lose this assertion here. In this case, you would have still hints to the prover, so it would be better than the sequential approach, but it would not be as scalable. So let's write this as, so you may end up with like a runtime curve which is somewhere like this. So you have a verification runtime which is kind of in the industrial design size.
One of the reasons that people use FPGAs is they are programmable. They're often making last minute changes. If you do make changes, do you have to go through this process again now?
The verification you definitely need to do again. The inductive invariant, in case you needed to do manual transformations to that, may be the same, but it depends on what the synthesis tool was doing.
Let's go back to one thing here. If you have full inductive variance, what does that buy you?
Yeah, so if you have the full inductive invariance, as I discussed earlier, the advantage is you get an approach which is even more scalable. So to put it in here, like let's say the full inductive invariant, the runtime may be more along those lines. And the goal is, of course, for this incomplete inductive invariant to be as close to the full inductive invariant as possible.
Tobias, well, thanks for a great explanation of a very complex subject.
You're welcome.